In this lecture, we're going to take the concept of a probability distribution and we're going to extend the concept that we examined as a discrete probability distribution to the scenario when we have a continuous random variable and therefore we need a continuous probability distribution. So recall that Prescott Bank example. Let's think about this in a slightly different way. When we first introduced the Prescott Bank example, we introduced a discrete distribution and we looked at it in a tabular form. And we talked about how we could actually compute probabilities by adding up the different cells in that distribution, and we could represent that in a numeric way. But we could also think about representing that distribution graphically, right, with a bar chart. And so the bar chart, the height of each bar represents the probabilities. And so if we were to think about computing the probability that either 2 or 3 tellers are busy at a particular time, that could be represented to a certain extent by just looking at the heights of those bars, right? We could measure the heights of those bars and then add those up, and that would give us the probability that we need. And so I want to continue with that idea just a little bit. Suppose now that we were in a scenario where we were interested in a variable that could take on any value across the entire real line. In that situation, rather than just having these bars, we might actually have something that looked more like a continuous curve that would go across that entire real line. And if we wanted to know the probability that that particular random variable, let's say, was between 2 and 3, with a discrete distribution, we just look at the heights of those bars and we add those up. The analogous thing in a continuous situation might be to look at the area under the curve. That's equivalent essentially to looking at the heights of those bars, right? How much area is actually between 2 and 3. And so that is what we're going to do when we move into continuous probability distributions. Instead of having discrete bars, discrete buckets where we can just add those values up, we're going to just smooth the entire thing out. We're going to draw a curve, and we're going to use that curve to help us compute probabilities. So in particular, suppose that we have a curve that looks like this, and you'll see shortly in the next lecture why we're going to use this particular form. But let's say this curve represents a probability distribution. If we look at the area under the curve, probabilities are represented as areas under the curve. So if I wanted to know the probability that my random variable, we'll call that random variable x, is between a and b, the way I would compute that probability is I would find the area under that curve, right? You may remember in integral calculus we can just integrate between a and b, and that would give us the area under the curve, and that would be equal to the probability. So to compute a probability with a continuous probability distribution, we're going to look at the area under the curve between those 2 points. If we looked at the area under the entire curve, right, if we looked at this entire thing and looked at the area under the entire curve, the area under the entire curve is equal to 1. So if we were to integrate across that entire real line, the area under that curve is equal to 1. Again, if you think about this, this is analogous to a discrete probability distribution where if you add up all of the probabilities, they have to add to 1. In this situation, if you look at the area under the entire curve, that would be the entire probability space. That area under the entire curve is equal to 1. Another interesting fact that you need to be aware of when we're looking at these continuous probability distributions is the probability that the random variable takes on exactly some value, let's call that c, is going to be 0 for any c. And if you think about it, that makes sense, right? Because this is a single point on the real line. The area under the curve at a single point is just 0. Or if you wanted to think about it from a frequency perspective, this is one point out of an infinite possibility of set of points that we could consider, and so 1 over infinity essentially would be equal to 0. And so the probability that x is exactly equal to some value is going to be 0 for a continuous probability distribution. And that has some implications. For example, when we're writing down probability statements, when we were dealing with discrete distributions, we had to be super careful about whether we were using strict probability or strict inequalities, or whether we were using non-strict inequalities, less than or equal to inequalities. So for example, if we look at this probability, the probability here we have a less than or equal to x and less than or equal to b. This is exactly the same as if we were to write the probability that A is strictly less than X and X is strictly less than B. Those are exactly the same thing because the probability that X is exactly equal to A or exactly equal to B is equal to 0. So with continuous probability distributions, we don't have the same concern that we have with discrete probability distributions of ensuring that we're very careful with those inequalities. In this case, less than or equal to and less than will be exactly the same because the probability that X is exactly equal to any value is equal to 0. So just keep that in mind as you begin to do probability computations with continuous distributions. So just to summarize, for continuous random variables, the probability that a continuous random variable is equal to some particular value is always equal to 0. We're going to use an equation or a formula to describe a curve that will define our continuous probability distribution. The area under that curve is going to be exactly equal to 1, and the probability that a random variable takes on a value between A and B is just the area under that curve between A and B. Before you get too concerned that we're going to do a lot of integral calculus, we primarily are going to be using tables and Excel functions to do these computations for us because we're going to focus on some very well-known probability distributions that have been studied and that have tools that will help us do those computations without having to do the calculus ourselves. But the idea is still the same. The probabilities that are being computed are based on an integral that allows us to compute the area underneath that curve. In the next lecture, we'll take a look at a particular continuous probability distribution called the normal distribution, which is probably the most important distribution in statistics. So we'll spend a little bit of time on the normal distribution and learn how to compute probabilities both with tables and using Excel.